OK, so first of all, put your hands up if you've ever tried using immutable on a struct in D. All right, have you quickly stopped doing that once you tried putting it into range? Yeah. OK, so let me explain where we as a company came from in this. So we are doing this, I think I talked about this a few DConfs ago, 3-layer design, where in the heart of it, when we're talking about business issues, we're doing something called domain-driven design, which is mostly from, I think, Java world, but it adapts very well to D. And part of the idea of it, like specified in the original document, part of the idea is that the business values that you're talking about describe the state of the real world at some point in time. So you're taking a snapshot, effectively, of some business case. You're taking a snapshot of, like, a train is arriving at a station, for instance, as the classic. And like, if the train moves on from that station, you don't change that object. You don't make any change to it ever. You just create a new one. And in effect, that makes every function that operates on the business level a pure function that has no effect on its parameters, that is completely side effect free, and its only effect on the rest of the program is the value that it returns. So this is very good. The advantage of it is that your code becomes very easy to test because it is fundamentally independent of the order in which you're running your tests. It makes it easy to predict what the system is going to do by looking at code, because you can see, if you're looking at some function, you can see all the changes, all the effects that it has directly in the function. You're never going to see a variable that is modified somewhere else without that, even if that variable is passed to that other location. The only thing that is going to change that variable is assignment. But that's a Walter?
Yeah. How is this different from functional programming?
It is not. Thank you. Very, very well observed. So at the domain level, we are basically doing functional programming, including the absolutely unreadable range code, which is very reminiscent of Haskell. But no, I kid. It's not that unreadable. You get used to it very, very easily. OK, that's next. You get used to it. There's an advantage there. And the advantage is that if you're using a lot of range functions, you're keeping a handle, as was previously mentioned, on your memory usage. Like, you can avoid allocations because instead of returning an array, you return the description of the array. And that's nice. So we want to do this statically if possible. We want not just to have a convention that we don't change any fields. We want it to be immediately obvious from the code that we are not changing any fields. So what we're doing traditionally in previous code is we have, for instance, a struct array container, and that has a private field. Every field in the struct is private, and if you know D, that is going to seem wrong. So, and we're doing a little underscore on that field that is just so it doesn't collide with the read accessor that we're also generating in a template. We used to write this by hand. This is an improvement on the status quo. So we just generate a public function that returns an int array, and because this is int, it's not mutable. It is mutable, but that function just does a dub. Because it has to do a dub because it cannot be certain that the caller is going to keep to the agreement. Actually, in this case, I think because I specifically tagged it as const, it's going to know that the caller can't modify it. But on the constructor call, we still need to do a dub for the same reason. So this is template-based, and templates are beautiful indeed. They're very nice, but they're not cheap. I mean, they are cheap, or they are objectively very cheap compared to any other language, but D makes it very easy and very tempting to use a lot of a good thing. And there's a lot of good things in D, like templates, that once you're doing them 100,000 times in a compile run, they start to add up a little. And there's another problem, which is, like, at this point, we have accumulated a good view of what in the compiler is likely to break on an update, what is going to cause issues. But there was an incremental process, and a lot of the changes in that code are workarounds for compiler issues. And what we would really want to be doing is the version on the right, which is just declared its struct as an immutable data type. So this is extremely visually easy. Like, you don't have to deal with const. We don't even have to do immutable. And I just realized that I forgot to explain to you what immutable actually is. I'm just going to take a quick sidetrack into that. So D, in the transition from D1 to D2, gained additional qualifiers on types, which is const and immutable. And the idea of it is there's a beautiful graph about that on the D website that I forgot to copy into my task, so just have to listen to me describe it. The idea of it is that const is the definition of a type that we promise not to mutate. And immutable is a type that cannot be mutated by anyone by any means. So you can implicitly convert a mutable data type to a const, but you cannot convert mutable to immutable because you as the caller may choose to mutate it at a later time, and then the contract would be broken. That's the idea of it. So when we're saying immutable struct, what we're hoping to see is that every variable that is defined with this type will not allow array to be modified by any means. We're not going to set a value in the array. We're not going to change the reference of the array. We're not going to make any changes to it. We're going to do literally pure programming. This has another advantage, which is that we heavily use invariant. And an invariant is something that you can put on a struct that checks if a relation between fields in the struct holds. And invariants are checked on constructor call, on destructor call, and on every method call twice, on entry and on exit. Where they are not checked, you may notice, is on assignment. So if you have a mutable array, you can write anything in there. And the first time you are going to notice that is if you're calling some method on it at some later time, or when the destructor runs, if you have a destructor. And so you're setting up, effectively, if you're mutating fields in a struct, you're setting up a time bomb that may explode at some later time you can't predict. So the right version avoids this completely because you can't change it. So you can't hit any invariant errors at any point. The only way to change it is to create a new value by a constructor call, which checks the invariant, and then replace the value that you currently have in one go. But now we come to the issue. So what we want to do is we want to use structs, and we want to use ranges. And as an additional fact, we want to use a lot of associative arrays, because in business code, associative arrays just tend to turn up very often. The problem is using immutable structs breaks a very large number of ranges in Phobos, and it also completely breaks associative arrays, which makes some amount of sense if you think about the fact that what we've said is a struct, which is a value type, is declared in a way that the memory that the struct occupies cannot be modified in the lifetime of the memory. That is the specific thing that immutable means. And so what you're doing is, for instance, if you just take an immutable struct and you pass it to max element, which is a Phobos function to get the element for which the predicate passed has the biggest value, then you get this very beautiful error. And for a while, I've been going around like posting these errors, these bug reports, and trying to fix them everywhere. But I've sort of given up on that because this is an intrinsic problem. It keeps happening. It's going to keep happening. And there's no stopping it. With every new function that is written, this error will reoccur. And the reason for that is that it is extremely powerfully intuitive, that it should work to just declare a variable and then assign a new value. Because C, after all, being multi-paradigm as it is, among other things, an imperative language. And to an imperative programmer, this is extremely natural. Now, to a functional programmer, the experience will just be that, OK, what you're going to do is you want to return a value, and then you want to switch between which two subfunctions you call depending on some parameter and just pass through the value change via returning a new value. The idea that you could modify a field is to a functional programmer unnatural. But we have the developer community that we have, and I'm not even going to think that's a bad thing. I think imperative programming can coexist with functional, that is, after all, the premise of D. But these types, immutable structs, will keep causing issues with that. This is the point of friction where the two worlds cannot coexist. Now, a common thing that Phobos thinks should work is you just use Unqual, which is a standard traits template, which is short for unqualified, because immutable const are type qualifiers. And so, OK, we have an immutable qualifier. Just to take the immutable qualifier off, then it's going to be mutable, right? Wrong. And this is actually very exciting because the way in which it goes wrong is hilarious. So when you declare an immutable struct, the immutable struct, if you just use the name of the struct, you have a qualifier of immutable on that struct. But as an additional fact, all the fields of the struct are themselves immutable. This is hilarious to me. So what you can do is you can call unqual on S, and what you get back is sort of a Voldemort type. It's a type that has no name in the compiler. It's not S. It's not S because S is immutable. What you get is non-immutable S. You can see that. We can do the type comparison. You can say it's not S. You're not getting S here. It's string of is S. It's not immutable S. The string of S is immutable S. And the string of small s, unqual s, is just s. But you can't do that. You can't overwrite it. Even though you'd think it should be immutable because you've stripped the immutable off, every individual field is still immutable. It's still toxic memory. It cannot be mutated. Now, what actually is the issue here that this is protecting us from? Now, as I already hinted at earlier, the problem to some extent is that immutable conflates two things. The first thing is that immutable is supposed to protect us from doing an assignment to a field of a variable directly in a way that could break the invariant of the type. So in a way that we create an intermediate state, possibly, or in somehow a corrupted state in which the type is in a state that has not passed through the constructor. Now, the actual thing that immutable does, it protects the memory from changing. And so the way that we can observe this, for instance, is if you have an immutable struct with a field, and we just define a variable of, I'm pretending this is a generic function so that it doesn't know that this is immutable, but it's going to notice very quickly. So we are just defining, the t in this case is just RS. So we're just defining a variable, and then we're taking a pointer to this field. And this pointer has the type of pointer to a mutable int. This doesn't have to be a pointer, it can be a reference. But a pointer makes it easier to see. So we have an immutable int, and now we take the value of that pointer, we read it from memory, and we just hold on to it for a sec. And then let's pretend we can overwrite that variable. Now we overwrite it with some other value, maybe our second parameter. And this has a different value in field. But the pointer is still live. The pointer is still ready to go off at any time. So we read it again. And then we have an immutable pointer, and we've now read it twice. And by the definition of immutable, both of those values have to be identical. But obviously, since we've just overwritten it, they are not identical. They cannot be identical. And so like part of the hope with immutable is that we would be able to do compiler optimizations, like I say we, the D community, not me personally, please. We'd be able to do compiler optimizations on the basis that if a value is read from an immutable pointer, for instance, the compiler could just assume that a second read from that pointer would return the same value. It could reuse a register. So, and that is why immutable is so very strict, because it has to defend us from, like if you compare with C++, for instance, where const is sort of a vague suggestion. In this case, the idea was very much learning from the fact that in C++ you cannot make optimizations like this, because you cannot rely for many reasons on const staying unchanged. But if you have an immutable pointer, that was supposed to be sacred. Like that was supposed to be something where you could read from, and that would, if that pointer was still valid, which the garbage collector would assure us it is, that would stay where it is. But if we weaken this assumption, now we're in hell. Now we have no assurance whatsoever. So we can't do that. Let's think about other options. There was an idea of something called, sorry, Walter?
Yeah, it seems to me that when you put unqualified on the struct, it unqualifies the struct, but it doesn't go and unqualify the members.
Yeah, exactly.
Okay, so that seems like a problem with the implementation of unqual, not really something breaking the rules.
As I understand it, this was deliberately changed. It was changed to be in this state.
I
don't know why, but I think there was a very good reason for it. And person in front might know it.
All right.
Sorry, one sec. Mike is on the way.
Thanks. I didn't know unqual worked like that, but I'm not surprised, and I think that should be by design like that. But we could write another version that also unqualifies the fields, but we're using reflection.
I will get to proposals. Don't worry.
All right.
So there was an idea of just having a separate head mute qualifier, because this has come up before. And the idea of that would be that everything that is by value in a type can be mutated if you put that qualifier on it. Aside from independent of everything else, independent of immutable, like immutable just gets pushed one layer down. Like every time you follow a reference, that reference stays immutable. The target of the reference stays immutable, but everything in front of it stays mutable. But that's not in the language at the moment, and we needed a solution at the moment. Now, the first time this came up was on the DNews group when we were talking about nullable a few years ago. And I think I put together this absolutely hilarious solution that is, I think, still in Phobos, which I called at the time a turducken type. For a bit of context for those non-Americans, there is an American dish where you take, I think, a duck, no, hang on, chicken, and you put it inside a duck and a chicken, thank you very much, and put the chicken inside the turkey, and then you cook the entire bundle of things, and at this point you stop wondering why America has an obesity epidemic, but that's neither here nor there. Sorry, it's a very cultural thing, I'm sorry. So and the idea here is that if we did the same thing, if we did this exact same thing, I'm not sure if the order here is correct to the actual dish, now that you said it. It just went in order of size as I mentioned it. I think the chicken is actually larger. Doesn't matter. It really doesn't matter. So the idea is you have your data type, and you pack it inside a union, and you pack the union inside a struct, and you store the struct in your data structure. And what this does is, hilariously, it just acts like head mute. Well, it acts like mutable in general. It completely makes it mutable. And the reason for that is that if it's in a union, it doesn't call the destructors. This was an intentional change. I want to be clear, this is not a bug. The idea is with the union, you don't have any idea which destructor you should actually be calling. So you're stripping out all that lifetime management just by virtue of putting it in a union. And if you put it in struct, and now this is a bug, you can call move in place on it even if it has immutable on it. Because move in place calls memcopy, and memcopy at the time used pointer casts that did not respect immutable. And so that worked for a while. I don't know what came of it, but it's obviously horrible, and I never want to see it again. So that was not a viable solution in the long term. Now, oh, yeah, this is a slide that had all this information on it. Very sorry. So then I started thinking again, what is the simplest thing that sort of does what we want in theory? And what we want to do is we want to be able to write a range function, and we want to have something of a variable definition on there where we can put an immutable in, and we can take an immutable back out, and we don't break the constantness guarantees for the compiler, and we don't cause any breakage in user code, but it just works. And so the very simplest idea of that would be just to have a void array, static void array. And you just say it's the size of the data, and when you want to put your data in that field, you just cast it to a head mute, and when you want to take it back out, you just cast it back. And that sort of works, but it's awkward because one of the things the garbage collector does is it knows, it has a pointer map. Like it has an idea with if you have a type, where is a pointer in that type, and where are stretches of things that cannot be pointers. And this is less important on 64 bits, but it's still present and it's still valuable. And I wanted to really avoid making the compiler's job harder. So then I started thinking, well, we're working in a language where we have a limited number of types. And like, D has a lot of types that you can define with structs and with aliases, and so it has a lot of magic. But the actual basic types at the compiler level are very small. They are enumerable. And so what it did was I just think, hey, why don't I just go through the list of types and I just define something equivalent with the right pointer layout for each of them. All right, so one of the advantages here is that D has some very nice conveniences for metaprogramming. One of them is that you can use private in a struct to prevent access to a field, but you can always use tuple of. You can always just look at the tuple of the values in the struct, and you can recurse over that. And I'm not sure, I think you maybe can't use that with classes, but classes don't matter. Classes are reference types. You just replace it with a pointer. And so for every single type in D, you can just define this very clean equivalence of something that looks like this type, but it's mutable. It's perfectly fine. We declare it as mutable, and it looks similar. We can cast to it. We don't get any breakage. And the garbage collector is happy. So we get this type, DeepUnqual, deep unqualified. And the idea is we are doing a recursion over the type we are given, and we just define a nice mutable equivalent type for each field in it, and the fields in that, and the fields in that, and so on. And there's some static assets in that just check, is it the same size as before? Yep. Has it have the same alignment as before? Yep. And if not, you just get a static error, and someone in the company runs to me to fix it. But that actually hasn't happened. It's been very well behaved in my experience. Now, this is not a type you want to use manually, because one of the rules we have for code review is you don't do you don't do reinterpret casts in domain code. And so this is kind of unpleasant. So there's actually a wrapper type in the library that just takes this DeepUnqual, and it just has a field DeepUnqual that you can't even look at it. It's private. And so you can put a value of some type into this field, and you can get a value back out. And this is important. You get the value by copy. And why is it important? The trick of this is, actually, I'm going to stay at the slide for a moment more. The idea is, again, we create, in effect, a mystery field. And what we have with this field is constraints. We have the constraint that we can put a value in it, and we can take a value back out. And we don't think about anything else with it. We don't know about anything else. It just does its thing by magic in the end. And internally, it uses DeepUnqual, but that really doesn't matter to us. What it matters is it's a variable that's always mutable. It's universally mutable, independent of type. Is this safe? Well, the thing is, it's safe. It is, as Gandalf famously said, is it secret? Is it safe? Yes, it is safe, precisely as long as you keep the type secret inside of this data structure. The problem with immutable, I remind you, is that we were able to observe an immutable pointer changing. And no pointer, no safety issues, right? No reference to any value inside the struct can be taken by any means. So, I mean, if you somehow do a tuple of magic, even if you do so, you just see a mutable field. You don't see an immutable field. You just see mutable field changing value, which is entirely normal and perfectly expected. The only point where the immutable comes in is when a value copy is made on return from get. And so this is the important thing. Because we can never observe any change in the value of an immutable field, in the value of a referenceable immutable field, then we're safe, basically. Now, the tricky bit, there are some tricky bits here. And once again, I've accidentally presaged the slide, turns out. Sorry. There's a bit of a tricky bit. And you can do some very, very magical things with structs. One of the reasons for copy constructors or for post-split constructors is that you were supposed with the struct to be able to do something like, I have a field I in the struct, and I have another field that's a pointer to that field. And even if I make a copy of that struct, that pointer is maintained because the constructor takes care of keeping it up to date. And that lets you do some very pretty things involving stuff like, I think, intrusive lists, anything that involves knowing where a data structure lives. You can not use any of those in types that you pass into rebindable. Because those assumptions, once you start moving memory somewhere where it wasn't declared, those assumptions break completely. Because you're doing the address that the value that gets returned from get lives at is a different address than the value that you put in. So your pointers will immediately be out of date. So that's an issue, but we don't use any of those things, so it's not an issue for us. Very good. Anyway, I think those cases are kind of rare, and well, I'll talk about proper solutions later. So what does this actually give us? Let's give some examples. So one of the things we have is a nullable where you can actually change the value that's stored in it for any type. So for instance, in this case, I've used const just because it's short on the slide. This is code that works today. You can grab the library from DAP today. So you can declare a nullable variable. The parameter can be anything. In this case, I've made it const, but you can have a type that is passed in by a user. And you can change it. You can change it to a new value. And you can delete it again. And the destructors on your internal type, if it has any destructors, will get called. The reference counts will be correct. So the number of copy constructor calls to destructor calls will match up. I have a very, very nasty internal data type called problematic. That's rebindable problematic as part of the library. That is absolutely hateful. It does everything you don't want a data type to do. It does disable this. It does. It counts the number of copy constructor calls. It has standard datetime system in it because I once had a bug about that and I was vindictive. But yeah, and that passes all the unit tests. So you can do associative arrays, and you can store immutable values in that associative array. And this is backed by a normal D associative array in the background that just has a rebindable value type. And you can just overwrite the same field. You can't do that at present because you can't find a working assignment op assignment overload for an immutable struct, but it works today. You just get the destructor call for the old field, you get a copy constructor call for the new field, and then it keeps going on like that with a new value in it. Okay, now obviously, even though this works, it's not what you would want to do, I think. Now, I have two proposals here, one that is kind of crazy, and one that I think is doable, but may in some be more crazy, and it's kind of up to you to decide which, if any of those, is the best way going forward. Now, the first one of those is actually that the problem is not that immutable proves too much. The problem is that immutable proves too little. And I have argued in chat for a long time that the problem is that we have much too early given users the ability to take a pointer to a field. And if we imagine that we were in a language where we couldn't take a pointer to a field, then we would be fine, right? We could just overwrite immutable memory all the time because nobody could catch us in the act. There's no compiler, there's no access that would break because there would not be any ability to read an immutable reference. It would always be an access to a data structure in a certain way that returned an immutable value. And so maybe we can exclude that. Like maybe we can define a struct that's stronger than an immutable struct. It's an rvalue struct. And I need to explain for the non-compiler developers in the room what an rvalue is. So the idea is if you have an assignment, just a variable assignment, then you have the left value of the assignment, which is the variable that you're changing, and you have a right value. It's very illustrative. So we call an L value anything that can be on the left side of an assignment operator. So anything where, in summary, basically anything that has an address in memory, and ignoring opAssign right now, so it's not quite that simple, but it was that simple in C, I think. So anything that can be on the left side of an assignment operator that has an address in memory is an L value, a left value. And anything that you cannot write take the address of this, that can only appear on the right side, that is solely an expression, is a right side value. And so the idea is that you define a right side value struct. You can never assign its fields by any means, except by assigning to a variable of the whole struct in one go. And so this is a pure data struct. You almost can't do anything with it. But what you can do, almost the only thing you can do is you can access its fields by read, by value copy, and you can overwrite the whole struct variable in one go. And that protects us from anything. It gets us back to the immutable struct, like in the beginning, because we can't violate the invariance. You can call the constructor. You can assign a new field. You can assign a new field of the whole struct. You cannot assign individual members. And one interesting thing to think of that is that it is a memoryless struct. Like it is not a struct that lives at a certain location in memory. It is a struct that only exists as a value. Right. Now, the slightly more practical example solution maybe is, well, why doesn't Unqual work? Why shouldn't Unqual work? I mean, Unqual should work, right? The idea, a lot of Phobos has the idea that you call Unqual and then you get a data type that can be mutated. But the problem is you get a data type that has methods on it that have immutable qualifiers and that expect this to be immutable. And none of those methods can now be called anymore. So why don't we do a halfway solution? And the halfway solution is we just make fields mutable again by default, even in a mutable struct. We do what we do currently, which is we just say immutable sets the default qualifier for the struct S. And so immutable, if you call Unqual on immutable struct S, you get a mutable struct S back out. But on any access to a field that is not a read access, you just have to implicitly cast it to an immutable struct first. And any method call, you have to implicitly cast it to an immutable struct first. And the trick of that is that all these Phobos functions, max element, for instance, they only do read calls. None of them want to do write, none of them even care about writing to individual fields. And so if we just allow read calls by this sort of round trip, then we end up in the situation where predicates on that struct still work. Like predicates that say, this field is the one that I want you to do the max element on. That still works, because you can convert that field to mutable and you can read it that way. But of course, you can't write to it, because then you will need to be converting it. What you have is a cast to immutable of a mutable struct. And the cast to immutable, a cast is a right side value. Again, you can't write to it anyways. So you sort of get the effect of a right side value struct for free, in a sense. Now, a problem with that is that it doesn't help us with classes. Because if you have a class, you can never cast it to an immutable class implicitly, because it's a reference type. But we don't use classes in domain code, so that's no problem for us. I'm not sure what the solution for that is. We could use, I guess, standard type const rebindable, which sort of solves the problem just for classes. But yeah, for now, libRebindable will do. So the code for that is available on dlang and on GitHub. And I've tagged it 1.0 because I think for something like 6 months or so we have been using this in production code. We've not run into any crashes or garbage collector issues. And since this is not exactly business-related code, thanks to Funkwerk, my employer, for letting me work on this. All right, I just noticed I finished very much early. So we have a lot of time for questions.
Cool. We do have one question from Discord already, from Hipreme. I'm probably pronouncing that wrong. Why don't we actually solve this at the language level?
Was this before the 2 slides that
I think so,
yeah.
But yeah, I mean, does that cover everything that needs to be solved, or is it just like a first step to getting a proper solution?
I think I have not given the language solutions as much thought as it deserves. And I do not want to say that these 2 approaches are exhaustive. Like this is, but as far as I can see from looking at it, each of them should solve the problem. And I think any fix that involves Unqual probably is better because then it works more easily with the code that is already available.
Yeah, and I personally have skin in the game because in game development, a large amount of data we use is actually immutable. So having stronger immutable is something I very definitely want. Attila's got his hand up down here. Question there first.
Yeah, so I'm not sure I understood what the problem is that we're trying to solve here, because ultimately if it's just trying to prevent memory being written after it has been marked as immutable or const, you could always, somebody could always use assembler and override that memory. I mean, I'm not sure what the problem.
I don't think you can use assembler in safe code. I mean, so to some extent, safe is not the only way to use the language, but like the assumption is that if the hope is that if we do like part of the reason why we don't use casts in domain code is there is a hope in our heart that if we do everything right and we do everything in the proper way and in the way the language commands of us, and if we address all deprecations immediately, then the code will never surprise us. And I think part of that is about that. Like the idea is that obviously you can always break everything. Obviously you can just break in with GDB and overwrite the field values directly. Like there was a beautiful post once about a company where they were talking about like what if there's data corruption if the power goes down, and one of the head developers I think was like, well, it's not an issue. We have a finally block. It's always going to be called. There's a certain level of perversity of the universe that is always going to stymie your attempts. The hope is what happens in the nice sane case is going to be something that doesn't surprise you.
I need to think about all of this a bit more carefully later because it's hard to do it now. But what is the difference between the proposed rvalue struct and using an immutable value?
Define immutable value for me?
So instead, like, take pointers out of the equation. What's the difference between an rvalue struct and a current immutable struct that uses only values of?
The one thing that you're allowed to do with an rvalue struct is overwrite the whole value at once as one value, as one object.
Okay, so that's definitely a difference.
And then you can't do that at the moment because it tries to copy over the fields, and the fields are marked as immutable in memory.
Okay.
And that's why rvalue relaxes the idea that struct fields exist at a location in memory, and that's why that's permitted.
Okay, thanks. The other thing is you had the immutable int star, and you could observe changes because of that. But that's nearly by construction because the pointer wasn't inside the immutable. If it were, you wouldn't be able to reassign the pointer.
Yeah, you don't have to reassign the pointer. You just have to be able to reassign the field it points at for this issue. This is not valid code, to be clear.
Right. So I'm not understanding what the
the idea is that if we did the naive thing and just allowed you to change an immutable variable, then this is what would break. This is what immutable is protecting us from. And so part of the idea of both proposals is to avoid this code from becoming possible.
All right, thanks.
Okay, I don't understand why we make an immutable on the struct. I will just make a mutable constructor, because if we want to construct the data, when we construct the data, we want to make it immutable, right?
Right.
So,
sorry.
So I was thinking, why don't now? Of course, I know it's a more general thing. But in this case, I will just make an inner struct with a range, and then return this because it has access to the iterator internally. I'm not sure, maybe I don't understand the problem.
Maybe I'm not understanding your question correctly.
When I use mutable, I don't declare them immutable. I just make it. I just construct them immutable when I construct them. And then, if I need an iterator, I'll put the iterator inside, and then return it as a const. Then you can iterate in the immutable, because you don't want to. If it's immutable, it's immutable, right? So you can return it as a const, a member inside the immutable.
Well, but
and it also works if it's mutable or const.
Well, but if you declare a field of that type, you're still going to be prevented from overwriting it. So I'm confused.
Okay, why would you overwrite it? I'm not sure I understand that.
Well, a bunch of code that's written even in Phobos now assumes that you will be able to overwrite a field if you've declared it with the right incantation.
Okay.
That's really the issue, and this is a very natural way of thinking. And like you can write your code in a way that it never runs into this issue, but you can't write Phobos in the way because you're not the one writing Phobos. You can't write dub libraries because, yeah. And I mean you can just write Haskell in D really. I mean you can just recursive calls everything, return everything, but I don't think decompilers make any guarantee about tail recursive calls. So.
Okay, yeah, because I don't use immutable like this. I use it in constructors only.
Yeah. What we really want is we want a user to be a developer to be able to look at an immutable data type that describes a domain object, a train or a journey or a visit, and want them to be able to reason about this code. For instance, we want to be able to have something like an invariant. If you have a journey with a bunch of legs, for instance, from London to Berlin to Oslo, and the legs are objects that always depart at a station and arrive at a station, then we want to be able to statically assure you that this is the arrival and departure station is the same.
Yeah, because I think the smart thing with the constructor is that you can make a const immutable and mutable constructor, and it would adapt to what you have. So you can make the same struct whatever you want.
Right, but we never ever want to see this field be mutable by any means. We want to completely
No, but I'm just saying, if you want to make it, then you can mute it, and then you can make a conversion, right?
Right. Yeah. Let's talk about that after, maybe, because I think I'm not getting some detail here. But let's talk about that after. Sorry.
So I think one way to go about addressing this is to say that the underlying issue is that the language conflates the lifetime of values with the lifetime of lexically scoped variables.
Yes.
And you could get rid of this issue, and then basically everything would just work the way you expect, and in safe code you would check the lifetimes correctly.
I think to some extent libRebindable is an attempt to do this in user space, but also to do it in the language itself becomes slightly painful if you're involving changes made in loops, because then you have to basically put a fine node construct in your language itself, and ain't nobody got time for that. But you can probably do it, but that would need severe surgery on the language, I think.
So I'm not sure I get the issue. So what do you say you would need additionally?
Sorry, one of the ways that for compiler developers, in the backend of a compiler, everything is basically immutable. And so one of the ways you handle that is if you have a loop variable, then what you say on every loop pass is that the value of this loop variable is a merge of the value from the last pass plus 1 and the initial value. So you're sort of carrying that value forward in time. This is called a phi node, like the Greek letter phi. And if you wanted to push immutable management or lifetime management into the language, to some extent, you need some way to be able to say, I'm replacing the lifetime of this value with a new lifetime. And for that, to some extent, you need to be able to say, because you can't say if case, assign value A, else assign value B. But you need to be able to say something like if case, declare a new value A, else declare a new value B, and then merge those two cases together somehow. Because otherwise, if you just give the developers complete freedom, then you lose all guarantees again.
Yeah, I'm not arguing for complete freedom. I'm arguing for doing it right.
Sorry, say that again, please. Last.
I'm not arguing for getting rid of the meaning of immutable. I'm just arguing for getting rid of some arbitrary conflations that are made.
Yeah. I'm just saying if you have a data type where you can say this data type now ends lifetime and then begins another lifetime, it's hard to use that correctly, I think, to some extent. And it's also, you still have to exclude pointers to it somehow. Because, I mean, you can say definitionally all the pointers are now invalidated, but that also does put kind of a lot of trust in the hands of developers. But it would be a solution, yes.
Yeah, I don't see where the trust is coming in. That's different from what we have now, but I guess we can take this offline.
No, the difference is that I still don't allow pointers by any means. I don't give you references into the struct by any means. Like the difference with the built-in rebindable, and the reason why I've named this rebindable, but I haven't pushed to put it into Phobos, into standard type const rebindable, is because standard type const rebindable currently returns the value that it contains as a reference, so that you can more easily reuse it, because it's really just a way to make classes head mutable. And if you're in some way giving the user access to a reference to your field, then all the pointer issues come back into play.
Yes, so you're trusting the user not to do this in lifetime management functions.
No, it's impossible not to do this it's impossible to do this with my library.
Okay.
Because you can only ever get a value. You can only ever get an rvalue view onto the field that's stored within. That's why it's safe. Does that make sense?
No, but as I said, let's take it offline.
All right. I have two questions. The first one being, how much... Here. If you, instead of making the struct immutable, if you disabled default construction and only provided immutable constructor, how much of your problem would that solve? I guess you tried already.
I have not actually tried it. This is a good question. I think you would still break a bunch of Phobos by doing it that way. Well, the problem really is that, for one, you could still do manual field writes, and that would get you the entire difficulty of the invariant safety backend. But even assuming you don't do that, I don't know to what extent like defining a manual lifetime management for structs is kind of, it's something you can do if you want to do a very specific magical thing like reference counting, but I'm not sure to what extent I trust it around in conjunction with pushing it through the standard library or pushing it through very long UFCS chains. I think it might, well, if it solved the problem, we'd probably try it, but since it doesn't prevent field access, it just gets us back to the initial example, which if you can now recognize, by the way, that this is correct because it doesn't give any one pointer access to the interior fields. So it's again that same thought about it.
Okay, yeah, it doesn't prevent field access, but it forces you to only instantiate immutable instances. So, but you would still have the problem with
yeah.
Phobos.
If you only instantiate immutable, yeah. Oh, but then the fields are, No, hang on. I think if you have immutable qualifier on the type, does Unqual then get you an immutable? Oh, that might be neat. Yeah, that might do it actually. Thank you very much. I'm gonna try that out.
The second thing is what you mentioned about Phobos, because I also had this problem. The algorithm indeed don't support const immutable or non-copyable types, and I think that's a problem we need to solve in Phobos.
The problem is that it is very easy to write unit tests that don't trigger this, or that don't probe this. And there's, as far as I can tell, there's not a habit of testing new code or testing existing code with immutable types. Or if there is, then you usually just do immutable int or something.
Then we need to make it an habit.
Like I tend to prefer solutions by which things become correct naturally without pressure. But yes, that would also help. Well, the problem is rather if you look at something like max element, actually, let's go back to that for a second. It is hard to think how you would even write this function without the ability to mutate fields or the ability to go into unbounded recursion. Like you want just, because we can't have a loop, because you can't. What you would need to do probably is have some way of iterating over the range and keeping track of the address, keeping track of the offset of the biggest value, but you can't do that because not every range is indexable. And so you're pretty much forced to go into unbounded recursion, and that way lies pain if you're not in optimizer mode.
Have you thought about maybe just declaring for the struct that you're using maybe an immutable to immutable OPS sign that's trusted and just cast immutable away?
Yeah, but at that point you're in trade-offs of perversity, honestly. Like the thing is that the way we're doing it now with libRebindable is that all the pain and all the awkwardness is, as the previous talk mentioned, encapsulated in this one magical data type about which we have thought and which we think is correct in what it does. And so the algorithms don't have to think about magic, and the data types don't have to think about this magic. And I think that's preferable, but it's probably easier if you just want to make some data type immutable to do that, yeah.
All right, I think we can do one more question if somebody's got one. Any takers? Nope. Going once, twice, 3 times, no more questions. Okay. Thank you, Mathis.